Hello everyone, it's August the 1st. Well, I think I won't have time today to dive into that problem, although we know how to do, because I have a little bit of work that I brought home, and I want to finish that today. So let's just get this one done. Maybe depending on how fast we can get it done, and then we'll deal with this later. So given n by n matrix, where each of the rows and columns is sorted in ascending order. Okay? Return the kth smallest element in the matrix. In a sorted order, not the kth distinct element. It must find a solution better than O(n) squared. So we have 1, 5, 9, 10, 11, 13, 12, 13, 15. So it says it's sorted in order on each rows and each columns, and I want to find the eighth. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay. Oh, it's n by n. Constant memory. O(n) time. No, I'm not ready for that. I mean, we can merge sort, right? Merge sort is going to be O(n). Well, actually, no. It's at O(n). Merge sort is going to be O(n) squared. Because I have to go through every single one. So, oh, I can merge. Can we merge K merge sort? Yeah, we look at the front, right? We use what's that you're thinking about? Priority queue. So we push the smallest out, and then put this one in, smallest out, this one in, smallest out, and then this one is done. Smallest out, smallest out, smallest out. So obviously O(n) log n. Yeah, so we do O(n) log n. Good enough. Good enough. Come on. O(n) log n is good enough. For today. Yeah. Okay. Now we just import head queue, heap queue, right? So what do we have? We need indices. They ask for O(n) memory. This is already not O(n) memory, because you have to create this. Nah, it's already not. Which, I mean, is fine, right? Which is fine. So we need to have a heap I in range n. So what we're gonna have is this. First one is going to be matrix I 0, and the second one is index, right? So that's the heap, and heap q dot heapify. We're gonna heap this thing, and then that's one. this in range k. All right, say val equal to val and index equal to heap q dot heap pop heap. Okay, so I pop it out, blah blah blah. I want to return val at the end. Okay, and then pop it out, index plus equal 1. If index is smaller than n, there's no n. If index is smaller than n, heap q dot heap push heap index already. Ooh, we need a 2. We need a row. And we need a man, you gotta be kidding me. We need 2. We need I and j. I and j. J is 0. So this is gonna be I and j. Right? J plus equal 1. If j is smaller, then we're gonna push matrix. I doesn't change. J. And then I and j. So we push this. If it's equal to n, that means we've done, then we just don't push. And eventually the last one will return. Okay. Let's run the test. Eight, 13. Okay. Matrix K. No. Case smallest to run it. Okay. So this is O n log n, right? I should try let's say 5. Let's try another one. All right, go for it. Okay. So that was good. Oh, so many different methods I used last time. So this is just very straightforward. 378. Priority queue. O n log n time. And O n space. It's not the best we want. Okay, so let's just go take a look at, I don't know, take a look at this. And let's take a look at everything and see why you use so many different methods. And I'm pretty sure that there's no change in the test case. It'll take a long time for this one to show up. $156. Oh, that's a naive solution. Heap solution. For V in row. That's a different type of heap. What is this? For v in row, the first row, we push minus, so the largest is at the top. And we say if the length is larger than k, that means, yeah, if it's larger than k, that means the largest one must not be, yeah? So we just pop it. And oh wow, okay. I did not realize, okay, this one works. What's the next one? Slower than the merge sort. Oh, that's the same as the other one. Ooh, this one. This is binary search. Oh. Okay, I'll take a look at this one later. Which is this one? Oh, I use merge sort. You don't have to. You can use the other one. This is NumPy. '86. Got one more test case today. So that actually is different. So this is the one. Binary search. Okay. So the goal is to find this, right? So what do? We find the smallest and the largest, and then we cut it in half, okay? So we cut it in half with binary search. Like on the first row, and binary search on the first column. And then what? And we know is lower and to the right, those are all larger than this. It's guaranteed to be larger than this. Actually, I don't know. Let's read. Smaller or equal to it. Smaller. Oh, smaller or equal. No, that's still not. If matrix ij is smaller or equal to the value, then all j plus 1, j and row I are smaller or equal. Oh, j plus 1. What? Yeah, it's smaller or equal to it, but how do you count that's smaller or equal to? if matrix ij is smaller or equal to a value, then all j plus 1 values j plus 1 value is not on the right side, man, it's on the left side. We count. We just count. So we're given a value, we go a line by line. For each one, we can binary search, right? And then, isn't that O n log n? Yeah, it's actually slower than the priority queue, but granted, it does not use additional space. So we go basically row by row. For each row, we do binary search, so we know how many is smaller than it, and then we add it together. If it's larger than k, that means the value we pick is too big. Then we pick a smaller. If it is smaller than k, then we pick a little bit larger. And eventually we shall arrive at a point where it is k. Because the case shall be 7, right? It shall be smaller or equal to. We can actually try this. Binary search. It's actually not. Yeah, I still like a heap. A heap looks better. So this one is binary search. Go row by row. Given a value, go row by row. Find the number of elements that are smaller or equal to the value, add them up. If the total count of values of numbers of nums smaller or equal to val is smaller than k, then we need to pick a larger value. Otherwise, we pick a smaller, and eventually we end when it is equal to. We end the search when the count is equal to actually k minus 1. That's how I'm thinking right now. Because the case 1, 2, 3, 4, 5, 6, 7, 8. So we have 7 values. Actually, hold on. 1, 2, 3, 4, 5, 6, 7, and 8, right? Smaller or equal to, yes, so 7 values, smaller or equal to. Okay. So we say what? Low, high equal to matrix 0, 0, matrix minus 1, minus 1. Okay? It's low and a high. And while low smaller than high, mid low plus high divided by 2, and for row in matrix index equals, what do we want? Smaller or equal to, so should be from bisect import bisect right. So I will go bisect right row and mid, right? So that value tells you how many. Right, so we're going to say count is 0. And then count plus equal to index. Right? Count plus equal to index. And I say if count is larger than k. Then we need to shrink, right? High equal to mid. Where do we... Man, this is always complicated. Yeah, I go high equals mid. If it's equal to k, shouldn't that be k minus 1, the target that you're looking for? If it's larger than k minus 1, if it's equal to k minus 1, then the mid is your value. Else, if it's smaller or equal to k minus 1, then low equals mid plus 1. So they will be the same when you do low plus 1, right? If we do low plus 1, which means smaller equal to k minus 1. If it's small, then so we say else low equals mid plus 1. And eventually I want to jump out. Actually, this one can go k minus 1, right? Then high equals to mid, and then we do, it's too small, go big, go big, go big. So eventually, we'll have a situation where count is smaller or equal to k minus 1. And then low will be plus 1. And then it jumps out. So current mid can be either smaller than k minus 1, and then we plus 1, jump out. Or it could be equal to, then we jump out. So we have two scenarios. Why don't we, let's say, we do larger equal to, and then, right, then it will be small. So then we just can return low. Let's try this. Yep, seem to be right. Now this, O, n, because we have to do n times, log m, where m equals max matrix minus mean matrix. O1 space. I think last time I didn't want to check the paper, nor do I want to check the paper today. What's the point? But just for fun. Oh, look at this! It's not right. 1, 2, 3, 4, 5. My output is 10. Hold on, this is not right. Five, should I 11? How does that happen? Mid count. How about low, high, mid count? Low and high, mid is 8. Count is 2. So we do 9, 15. Mid is 12. Count is 6. Count is 6. 12. 1, 2, 3, 4, 5, 6. Count. How would the count only be 6? Oh, yes, it is 6. 1, 2, 3, 6. Okay, so it's too big. So we do 9 and 12. 9 and 12, we get 10. Okay, get 10 is 1, 2, 3, 4. So it's too small. It's 4. Count is 4. Right, 10. Count is 4. And the target is 4. So it says larger equal to. So high stay at 10. High stayed at 10. That seemed to be the problem. I think so. It could be 10 is 10. I have 4. Oh, that's including. That's including. The count is including. It's not like in front. It's including. I hope these two don't arrow out. Okay. Try this. Actually, that would be actually a good practice, right? One, two, three. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have 10. Okay, that looks good. Oh, it's faster. N log n, n log m. I don't know why it's faster. All right. So yeah, we done this. Pretty good. (1984). The paper is from 1984. Information processing. Divide and conquer. Selectioning x plus y and matrices with sorted rows and columns. Let A be a matrix of reals and sorted rows and columns. And K an integer. I present O(n) time algorithm selecting kth smallest element of A. multiplication sum is such. And log in, yeah. Oi, oi. Computer rank. My lord, I don't want to read this. But they say there's O1, ON. Yeah, okay. Alright, that'll be it. Yeah, I don't have any gana to go for this one today. I'll see you guys tomorrow. Adios.